Ring of charge. Electric field due to a ring of charge that lies in the YZ plane and is centered on the x-axis is given as this. There's the electric field. We actually calculated that over in the presentation. Find the distance x along the x-axis where the electric field is a maximum. What is the value of the electric field at the distance found in part A? Sketch the electric field on the plus x-axis as a function of x. Find the distance x where the electric field is a maximum. Whenever you want to find a maximum or a minimum, you take the first derivative and set it equal to 0. So that's what we're doing here. So dE dx equals 0. Make sure you make this statement, because even if you don't do all this stuff, that could get you a point showing that you at least knew how to find it. You put it in there. There's my electric field. And what's the first thing you do? Pull all the constants out, so just try and make it simpler. So I've got the q over 4 pi epsilon 0 out here. And now I have to use the product rule in calculus, right? Because I've got x here, and I've also got the x over here in the parentheses. And I think there's a chain rule involved too. Again, you ask your math teacher. I know how to do it, just don't know the names. So the first thing I do is I keep x constant. And you know what? Let me erase some stuff there so it makes it more clear what I'm talking about. I'm going to keep x constant. There it is. And take the derivative of this guy. So you bring the negative 3/2 down in front of it. You take the entire parentheses, put it back there, and reduce this negative 3/2 by 1. So you get negative 5/2. But now you also have to take the derivative of what's inside the parentheses, and that's 2x. Next, I keep this whole thing constant, and I take the derivative of the guy in front. So d by dx of x is just 1, so the whole parentheses comes down like that. And once again, I'll erase. So please, before you go to the next slide, make sure your calculus skills can handle this for you, okay? So practice it a little bit. And what am I doing here? I'm multiplying through by -1, get rid of this, and then I'm going to keep him on the left side, and on the right side, that term goes over with a -1, multiply by -1, it gets to be positive. So maybe I'm over-explaining this. I just put the two expressions on either side of the equal sign. So again, pause this, practice it, and then go on to the next. Continuing the work, continuing the algebra, this came over from the previous slide. And then I just do a little more algebra, and I just multiply all this through, okay? The 2 very nicely cancels out, and I'm left with this expression. So I'm almost there. And then I'm going to divide the x squared plus r squared parentheses, okay? So if I divide both sides by x squared plus r squared to the -5/2, cancels out here, and this now becomes just x squared plus r squared. That's kind of nice. So I have 3x squared equals x squared plus r squared. One more step, x is equal to r over the square root of 2. And that's where you're going to find either a minimum or a maximum. So let's go on to the next slide and discuss that. To be truly mathematically rigorous, we should calculate the second derivative of the electric field. And if it is less than 0, we found a maximum. Takes a lot of time, and this is a physics test, not a calculus test. So you can kind of guess that they're not asking you to do that. But let's see if there's some physics stuff you can do to help make you feel better that we actually found a maximum. What you can do, if x is equal to 0, what's the electric field equal to? 0. So right at the origin, it's 0. And then also, as x gets very large, as you go to infinity, this term here will dominate that one. And what you're going to do is find, let's see, so if we get rid of the r squared, x squared to the 3/2, that's going to be x cubed. You have an x on top, so that'll be 1 over x squared. So when you get to infinity, once again, you're going to be at a minimum. And then if you just increase x a little bit, you see that it starts going up. So you're going to kind of guess that your field is going to look like that. So that should make you feel a little bit comfortable that you did find the maximum. But please don't go doing the second derivative. Too much time, and they're not going to be looking for that. Now we want to find the value of the electric field at the maximum point. So we have our x right over here. We plug that into this equation. And again, this is just some slightly messy algebra. This is where it's very important to spread your work out. You're not allowed to bring extra paper into the exam, but they do give you room on the exam sheet. So once again, use pencil. Because if you start down a trail and you find out it's all messed up, you don't really have a lot of room to do it again. But if you erase it, then you can just reuse the space. So you substitute in for x, there's an x squared. You do some algebra, and then we'll continue on the next slide with some more algebra. And here's our continuation, finding Emax. That's from the last slide. You keep doing simplification until finally you find that Emax is equal to this term. So I'm not going to go over each step. Please figure it out, and if you find a mistake, please send it into NJCTL so we can fix it. So that's our maximum value of the electric field. Sketch the electric field on the x-axis as a function of x. So we've actually done it both on a negative x and the positive x side. We talked earlier how it looks like you're going to go up and then down, so we kind of sketch that in. We show at what point of x that is, and we show what the value of the electric field is. Now, one thing you might just say is, why are you showing a negative electric field here and a positive here? Isn't this a positive charge? Shouldn't the field be positive on both sides? It's a positively charged ring. Yes, it is, and this is where math sometimes doesn't show you what physically is happening. Because if you go on this left side here, what are your values of x going to be? They're going to be negative, okay? So when I put a negative value of x into my electric field, it's going to show a positive number. So that's just an artifact of negative x's are over here, positive are over here. But if you had a meter and you wanted to measure the electric field on both sides, it would absolutely be positive. Here's how I figured out the sketch. Well, one way to do it is use a graphing calculator, which are allowed on the exam. The problem is, unless you're very quick with it, you may spend too much time on it, and there's a quicker way to do it. And of course, for this one, I just use the graphing software, graph-free.com. But let's see, we know we have a maximum. So right away, you can put a maximum point right here, and you would put r over the square root of 2, and you would list what the electric field is. So when x is smaller than r, what happens? When x is very small, this is going to behave like a linear function, right? Because you're squaring a tiny number, it kind of goes away. So for small x, you have basically a linear type thing. So it's linear, but it's curving a little bit, because the more x gets greater, the more the square terms gets to play a game. At the top, we hit a maximum, and then we know we decrease, but what do we decrease? Why did I draw it like that and not a straight line? Again, well, let's erase up here so you can see. What's going on, as x gets greater, eventually r squared won't be so important, so we can just kind of ignore him. Now what do I have? Let's not worry about the constants. I have x on top, and on the bottom I have x squared to the 3/2 power. Well, what's that equal to? It's x over x squared, square root is x, cube it, x cubed. So you have x over x cubed. You're going to fall off as 1 over x squared. So that's why, no straight line there. We drew it like this, and then the electric field died off to 0 at some point near infinity. What is the College Board asking for when they ask you to graph something? First of all, and this comes right off their website, when they say sketch, they mean draw a graph that illustrates key trends in a particular relationship, such as slope, curvature, intercepts, or asymptotes. Numerical scaling or specific data points are not required in the sketch. So if we were just sketching that previous problem, this would have been totally adequate. However, be careful. Sometimes in the problem it'll say something like, explicitly label any intercepts, asymptotes, maxima, or minima with numerical values or algebraic expressions as appropriate. And you can see that's what we did on the previous slide. We put the numbers in. So watch what they ask for. And just a quick word on the specific data points. We certainly didn't have any in this problem, but they'll give you experimental problems where they say somebody took a reading and at various distances, here's the different electric field values, plot it. That's when you're putting in the specific data points. This problem was worded and it only called for a sketch, but I'm not the College Board. However, we put in the extra information about the maximum, minimum, and asymptotes to meet the extra requirements that could show up in a free response question on the exam. So the recommendation, if you have the information, put it in the graph to ensure that the grader has a complete picture of your knowledge. Also, and this is mandatory for everything, every graph, label the axes, include the units as appropriate or if appropriate, and make sure you put a title on it. That can get you a couple points or conversely lose you a couple.